Okay, right. So I hope everyone can hear me online as well. Uh, so my name is Isadora. I am a postdoc working with Marc-Olivier Renou at INRIA, like just your neighbors. And I want to present to you some results that we put on arXiv a couple months ago uh, regarding a quantum advantage in distributed computing. Um, just before we start, I think it's interesting to talk about the collaboration that has put out this work. So it's many different groups. So we're here on the French side. We have some people in Japan, a lot of people in Italy, and most important, some people in Finland.
Okay, perfect. Okay, then welcome to our first weekly meeting of the Phoenix. I see it as continuation of what we had last year. So nothing new. I sent the agenda yesterday and Marcos suggested.
Okay. Voilà. Right.
Rajoutez par Nico.
Well, I'll just go on. And so in this group, we are trying to take the paradigm of distributed computing and applying this to quantum. So the way we're doing is that people in Finland, mostly they're doing the distributed computing part while we're doing the quantum part. And this works very well because we're physicists. We don't know that much about computer science. And the people on the other side, they're computer science. So they don't know much about quantum. And this way we can do what we do best in such a way that at the end the result is something that makes sense at least. So I'm a member of FICUS, which, as I said, is a group just around the corner. Our group is comprised of 3 PIs, 4 postdocs. Right now we have 7, maybe 8 PhD students. I don't know how many master students at this point. And if we look at the most local view, we are working under the guidance of Marc-Olivier. We are the 2 postdocs involved in this whole work. We have a bunch of PhD students, among them Luis, and in collaboration from some people from Nokia Bell Labs, so Ludovic and Remy. And hopefully, if everything goes right, 3 of us involved in the project. We're going next year to Finland to spend a month with people on the computer science part and drive this collaboration forward. So now if I want to talk about our result itself, I think maybe I should start discussing what is distributed computing. So when we do regular computing, we're assuming that you have a central processing unit that is going to receive the input for some kind of problem. It's going to process it on its own, and then it's going to spit the answer. However, for bigger problems, for more complicated problems, this kind of thing gets really out of hand. So what we have in most cases in our real life, what you have is a scenario where you have distributed computing. So you have several processing units that are spread around. They are allowed to communicate with each other, and they are going to collectively get the inputs for the problem, and they are going to coordinate, communicate in such a way that they can together produce the output of the problem. So this is the kind of thing you have already when you stream some movie online, when you do internet banking, when you play some games. So behind your seamless experience is a very complex network of distributed computing working in the best way possible such that you don't even realize there's something very complicated going on. So when you think of these scenarios of distributed computing, we can think of this in an abstract way, where every processing unit is a node on a graph. And whenever the nodes are allowed to communicate, you connect them by some edge. So one example of one of such distributed tasks is you have many phones, people with phones in France, and you have many, many antennas that are spread around the country. So when two people pick up the phone and they talk to each other, they have to be assigned one specific bandwidth for communication, and it has to be unique. Otherwise, you're going to interfere with the conversation that other people are having. However, your phone is only going to connect to the antenna that is closest to you. So now, how are we going to find a way such that two people call in from very far away, connecting to antennas that are not the same? How are you going to assign the correct bandwidth to each of these pairs of phones in an efficient way? And when I say in an efficient way, what I'm interested in is with the as little communication between the nodes, in this case, as little communication between the antennas as possible, because this is the kind of thing that is going to slow down the process. Every time I have to communicate between my processing units, this is the kind of thing that I want to avoid. And if you think about this bandwidth assignment problem, this is, you can see this as a coloring problem. So I have many nodes on a graph, and I want to assign colors to each of these nodes according to some rule. So it could be, for instance, that no neighbors have the same color. So the kinds of problems that we're dealing with in distributed computing, they are very similar to coloring problems. The difference is that they are much bigger, much more complicated, and it's going to take a lot more power to solve this kind of problems, right? So let us first look into a much simpler problem so that I can introduce to you what is the kind of drawbacks that you face when you're trying to do distributed computing. So you can think, for instance, of a loop where every node is connected to its neighbors, and I want to assign two colors to this loop such that no neighbor shares a color. And the way you would do this naively would be just to have some central unit that is going to assign the color to each of the nodes. So this central administrator sees the whole network, and with this whole information, it can assign the correct colors. The problem is, in these settings, in these scenarios of distributed computing, you do not have a central administrator. You cannot have some, because the network is so big, you cannot assume that you have someone who's able to see everything, take all the processing on itself, and then assign the correct colors. This is a setting where we can actually only assume that a node has the information that is local to it. So I know my inputs, I know the results from whatever process I'm doing, and I know I have neighbors. So in this case, this node knows it has two neighbors, but every information that is outside this region is not something you can count on. So if you obey this suppositions, the kind of problem that you are interested in this setting, they are problems that are called LCL. So they are locally checkable labeling problems. So these are problems such as the graph coloring problem. These are problems that are very easy to check if you have the right answer. If every node looks at its own color and the color of its two neighbors, and checks that this is valid, this is not contradicting the rules of coloring, and everyone does the same, everyone checks that is correct, then you know that the global answer is correct. So these are problems that can be locally checked. So they are problems that can be very hard to find the answer, but if you have a proposed answer, should be easy to check. And in this scenario, when we're analyzing LCL problems, what we're interested in is how many rounds of communications are needed to find this answer. Quantum enters this game for quantum distributed computing when we ask ourselves, okay, so what if instead of having a bunch of classical processing units spread around the country that are allowed to share a classical communication channel, so I can send bits to my neighbors and do whatever computation I want on my classical computer, what are the advantages that I could get if I were to consider a bunch of quantum computers that can communicate through a quantum channel. So now, instead of sending zeros and ones to my neighbors, I can actually send a quantum state. And what we are interested in, so can we find a problem, an LCL problem, that when you consider a quantum setting, you get an advantage when compared to the classical setting? By advantage, I mean a scenario, a problem that I can solve faster with quantum than I would have solved with classical. And one example for where this kind of problem is going to be very relevant is in the hopefully near future when we have quantum cryptography. So cryptography is a task that is performed between two agents. However, these agents in the future, they are going to be embedded in a quantum network, a possibly very complicated quantum network. So if we have, for instance, two agents in this network that want to establish secure communication, you have to find a route between these this pair of red agents, but I also would have to find a route for a pair of green agents that want to communicate at the same time. And then if you also have a third pair of purple agents that are also trying to communicate, then the challenge is, how do I find a valid route between all these people wanting to communicate such that they don't interfere with each other? And you can see that this is also in some way a coloring problem. At the end, this is also going to be some kind of LCL problem that we are going to face in the future once we are able to establish quantum cryptography. So before our work, what we knew so far was that there was no quantum advantage. All we had found before, and by the way I say collaborators, so our group has been working on this before, and all they had found was a negative example. So what they had provided was a situation, a problem where you do not get any quantum advantage. And just to explain very fast what was this negative result, it's so you give me a graph, and I tell you that this graph can be colored with a certain number of colors, say 3 colors, using a certain number of steps. Now, if I allow more colors in the coloring problem, the problem gets easier. So if instead of only having 3 problems to color a certain graph, now I have 4 colors, this should be easier, which means you should be able to do this possibly faster. You would need fewer communication rounds to color it. And what they showed is that how faster you color this graph is irrelevant if you're doing a quantum or a classical algorithm. So you get an advantage because you have more colors, but this advantage is the same if you do it quantum or classically. So no quantum advantage in the faster coloring problem. What we were able to provide, and it's this paper that has been put on arXiv recently, it's the first local problem where you have a proper quantum advantage. So I'm going to describe to you a task, a network task, that if you do this classically, this is going to need omega of delta rounds, where delta is the degree of the graph. So it's like how many neighbors each node has. While if you do it the quantum way, this is constant. You only need 1 step of quantum communication to solve the whole problem. Now, for this part, I will try to do this the most didactic way. So I would actually prefer if you stop me at some point if you don't understand anything, but now we're going to do the quantum part. So let's first look into a simpler problem that I think is going to give the right intuition to why this is the kind of task that can be solved very fast with quantum, but classically it's going to take a while. And this first problem that we're going to look into is called the CHSH game. So this is a game where you have 2 agents. You have Alice and Bob. They are very far away from each other. And each of them is going to get an input. So Alice is going to get some input X, a bit X, and Bob is going to get another input Y. Their task is to output A for Alice and B for Bob, such that they obey this relation. So X times Y should be A plus B modulo 2. So what this task is saying is they're very far away from each other, so there's no influence between them in some sense. If either Alice or Bob gets input 0, their outputs should be the same. So they have to coordinate somehow such that their outputs are the same. However, if both of them receive input 1, their outputs should be different. And you can convince yourself pretty easily, I think, that if you do this classically, so if you think of a strategy that Alice and Bob should follow, you can only hope for a 75% chance of winning, because there are 4 different outcomes, 4 different situations. So both Alice and Bob get 0, one gets 1, the other gets 1, or both get 1. These are the 4 input scenarios. And you can only hope to win 3 of them at the same time if you're thinking of this classically. This is something that is known. We also know that if you allow for a quantum strategy in this scenario, you get an improvement. You can actually solve this problem with around 85% chance. And by a quantum strategy, I mean that if Alice and Bob could, for instance, share a maximally entangled state and perform quantum measurements on these states, then the outputs that they produce have 85% chances of obeying the winning condition. Now, if you now allow for a non-signaling strategy, there's a way that you can always win this game. And by non-signaling strategy, I mean any strategy that in an intuitive way does not violate special relativity. So it has to be a strategy that does not allow communication between Alice and Bob in a hand-wavy way, but I'm not going to elaborate more on that. So because you can only win this game with 75% chances in the classical way, if you want to perform this task, you need to allow some kind of communication between Alice and Bob. So for instance, if you allow Alice to communicate once with Bob, Alice could, for instance, send to Bob her input and whatever output she chose. And then Bob, with this information and his input, he can pick the proper output B such that the winning condition is obeyed. So if you want to win the CHSH game in a classical way, you need 1 round of communication. If you want to do this in the non-signaling way, there is actually a way where you need no communication, basically. And that is the case if you are allowed to share what we call a PR box. So in a very general way, this PR box is some kind of resource that, as far as we know, does not exist in nature. It's just a theoretical, so far at least, a theoretical construction that is very powerful, but still obeys special relativity. So it does not violate non-signaling, but we know that if you have such of these PR boxes, you can actually win this game always. So if you had a PR box, you would need no communication whatsoever to win this game. Now, if I take this game, which is a game that is played between 2 agents, Alice and Bob, and put this into a very complex network, then you would play some kind of network CHSH game. So
just a question, yes. What does this box do?
So
mathematically, it doesn't exist?
Right. So mathematically, what this box does is exactly obey those winning correlations. And so it's 100% a theoretical construct, but we know that obeying these correlations is still non-signaling. You would still not violate special relativity. Yes.
For me, it's difficult, but we will discuss later.
Well,
it's difficult to imagine.
We can. So
it cannot work in real world. But,
well,
it's difficult for me to imagine that if the law of nature will be different, but still be in an equation with the special relativity. It's difficult for me to imagine
right.
It works.
Yes, but then the nice thing about this box is that even though it is very powerful, that it can produce these correlations, it does not violate what we understand as the laws of nature. It is beyond quantum. So in this sense, it does, but it does not violate anything fundamental. It does not violate special relativity. It would not allow for instantaneous communication. So it's very powerful, but it could exist. We don't know. We don't think so, but it could exist. So I think you had a question.
Yeah, the rule that you use for the wind, is this arbitrary? I can put whatever rule in the PR box?
No, so the PR box is one specific box that obeys this specific condition. You can create some other box, call it your name box, and this box will do whatever you want. Right. Right. So I can think of this game being played between two players. So you have these two players here connected by a channel, and they're going to play the CHSH game together. Now, if I put this into a network, I could actually think that, okay, every player is in fact going to play 3 CHSH games. I have 3 neighbors, and I'm going to play 1 CHSH game with each of them. However, each of my neighbors is also going to play this game with 3 neighbors. So they're going to play with me and with 2 other neighbors. And these 2 neighbors play their own CHSH. It goes on and on as much as you want. So in this network where everyone is playing the game with 3 neighbors, we're calling this is a CHSH network game, right? And this is the task that can be done faster with quantum, but classically it can take a while. Because every player is going to play a bunch of CHSH games, but I don't want them to be independent. I want these games to be somehow interconnected. How are they interconnected? So let's take a closer look at one agent that is playing the CHSH game. So I am going to play this game with 3 of my neighbors, which means that for my first game, I will have some kind of input x1, and I will have to produce some output a1. So this is my first game. I will also play a second game where I have to provide some input to this game and produce some output, and the same for my third game. Now, these games are not independent, and what I mean by that is that the input to my second game is the output for my first game. So I play my first game, I get a result, and then I forward this result to my second game. I will do the same thing between my second and my third game. So I have to play my second game and then play my third game. And just one detail, the input for the first game is already 1. It's always 1, just because it's easier to think of these problems as problems without input. The input is fixed. Now, the goal here, remember, is to win this game as fast as possible. So I want as little communication as possible with my neighbors, such that I can produce the correct answers. And the thing is that classically, you need 3 steps of communications to win this game, because I need 1 step of communication with my first neighbor to win my first game. Then only after I won my first game, I have an input for my second game. For my second game, I will need another step of communication. I will have to send some kind of information to my partner such that we can win the game. And then the same thing for my third game, which means, yes.
Is the ordering something that has to be symmetric between different agents, or does each agent have his own ordering, and the same edge can be the first one on the left, on the right, and the third one on the left?
So you have freedom to define the setting that you're using. The one we're using, the ordering is consistent. So I'm playing my first game with someone who is also playing their first game, and my second game with someone who's also playing their second game. You can find a consistent way to form the game. So you're right, the game is defined by a network and a numbering of my ports that is consistent with my neighbors. But yes.
Has the network got any incitement?
So the network got any what, sorry?
Is it a tree? Or is
It's a tree, yes, it's going to be a regular tree because everyone has the same number of neighbors. Yes, so in this case, it's going to be a 3 regular tree. Yes.
But does the problem make sense for a general graph, or it only makes sense for a tree?
The problem itself makes sense for any graph, but I'm not sure you would get I don't know if you would get an advantage for any graph. Right.
But then your graph is infinite because you need at each time to have 3 neighbors. So it's an infinite graph.
In our case, it doesn't make a difference.
Yeah, I understand.
But we are thinking of infinite graphs, yes, just so we don't have to think about what happens at the border.
Yeah.
But for this specific case, it doesn't matter.
Yeah.
Right.
This means that there are nodes in your case that play less than 3 games.
So in our case, no, because we're thinking it never ends.
Okay,
So, but if it was, yes, a finite graph, someone be at the border and would play only 2 games or only 1 game. Yes. But the point is, for these people, it would only be easier to win. We have to look at the hardest node, and which would be somewhere in the middle of the tree.
So this is the 3 regular tree.
Yes. Yes.
Fully complete 3 regular.
Yes. Yes. Right, so maybe from this explanation, you can see that classically, there's a hand wavy explanation. You would need 3 steps of communication to win the game, because there's no way to go around it. You have to play your first game first, your second game second, and your third game last. And for each of these games, because you're doing it in a classical way, and there's no classical way of winning the CHSH game, you need to communicate once with every neighbor. Now, if we do it the non-signaling way, so suppose I had peer boxes, suppose they existed and I could control them, I would actually only need 1 step of non-signaling communication to win the game. I could use this step. So on my lab, I prepare 3 peer boxes, as you could, for instance, prepare 3 quantum states. I will send half of each of these peer boxes to my 3 neighbors. Then I'm going to establish this network of peer boxes connecting neighbors. And if I have peer boxes, remember, I don't need any additional communication to win the game. So I would need 1 step of communication, which would be the step of sending the peer boxes out. But apart from that, I would not need any more communication. So I could play my first game first without communication, then play my second game without communication, play my last game without communication. So this is just to give an intuition of the advantage that you have when you're considering classical resources and a classical channel to when you're considering non-signaling resources and a non-signaling channel. You could go from needing 3 steps of communication for 3 regular trees to needing only 1 step of communication, if that's clear. Yes.
So I'm confused now with the sending of peer boxes, because one of them is going to be sent by this node, but the other is going to be sent by the neighbor node.
Mm-hmm.
So how do you make sure that those 2 peer boxes are the same one?
You could, for instance, so you could do, for instance, everyone is going to prepare 3 peer boxes, and everyone is going to send a PR box to your neighbors. So what would happen is that everyone would actually have two PR boxes connecting neighbors.
Yes.
Then how do we decide which one to discard? With this PR box, I could have sent a random real number between 0 and 1. And then my neighbor would also send it to me. And I could look at the number I drew, the number my neighbor drew, and whoever got the highest number gets to keep the PR box. So if I knew, okay, I got the smallest number, we're going to discard the PR box that I send. We're going to keep the PR box that my neighbor sent, for instance. Does that make sense?
Communication.
Sorry.
There is always a chance that the two random numbers are equal.
Oh, well, if they are.
Probability is 0, but.
Okay, but all right. If you assume that the probability of sampling two random numbers, real numbers being the same is 0, then this works. But you're right. If you're assuming that this measure 0 probability is considerable, then that doesn't work. But then I think lots of stuff would not work either. But you're right. Okay. If they get the same number, which will happen never, you have a problem. But I think we can take our chances.
Yeah, it's a theoretical anyway. So.
No, but this part is not theory. These are real numbers. Like it's something that you can draw, right?
Well, shouldn't the PR boxes be the same? Like the rooms seem symmetrical, so probably the PR boxes are equal.
Yeah, they're equal. The problem is the answers that the PR box is going to give. They are always going to be right, but they are not unique. So, for instance, if both parties put 0 on the PR box, the PR box is going to output either 0, 0 or 1, 1. If I have two PR boxes, it could be that for one I get 0 and for the other I get 1. I know it's going to be a correct answer, but it's not going to be consistent. So we have to have only one. But this is something you can do if you have a random number generator, which, okay, it's a point that could be contested.
And can you merge two PR boxes?
So you can do that, but what you get at the end is not a PR box. So you could do a convex mixture of two PR boxes, but the result is not a PR box.
I have another question, in fact. So if we look at the figures on your slide, the first input is x equal to 1. So it is true for all the nodes?
Yes, yes.
So all the nodes know that they start with x equal to 1.
That's true.
So they can choose a1 equal to 1 everyone.
So if
so
they
it will win the SH problems, and then you can still go on without communication.
So the problem is that if everyone gets 1 for the first game, the output that they have to produce is one outputs 1, but the other has to output 0. They're going to be different. Yes.
Yeah.
Yes. And then from the second round on, it's a mystery. Who knows? Right.
So I thought there should be. I do not remember in fact the exact rule.
No, you're right.
There should be equal.
Yes, but that's why we chose x equals 1, because yes.
I understand now.
Right. So anything else so far? Because this is the core of what I want. This is the intuition of what I want to show. I'll go further with other stuff, but this is just more of the same. The core is here. The point is that this is a task that is very hard in some sense for classical. You need a lot of communication. For non-signaling, this is very easy. Because then I'm going to show you a game that is very hard for classical, but very easy for quantum. And the reason I decided to show this one first is because this is easy to draw. The other one you're going to see is very messy. So if you're looking at the non-signaling CHSH network, you need communications so you need, in this case, 3 rounds of communication. So it's the degree of the graph, it's the number of neighbors that you have to win this game. And if you do it in the non-signaling way, you can solve it with only 1 round, which is the round to send PR boxes to your neighbors, and then no more communication.
Just a last question. I'm not sure I see why you can't have loops with your solution. It's harder to set up the graphs. You need constraints on the edges being all labeled. But with your solution, it doesn't appear as if loops are an issue.
Right. So the thing is, if I had, for instance, if this here was a closed loop, so it's just that you would have to define a different game. So what would be the new order? I would then, it's hard. Okay, maybe I can.
You could label all the edges 1, 2, 3 with the constraint that every vertex has one edge, 1, 2 edge, 1, 3 edge, and then you could run your game similarly.
No.
Locally, it's the same game.
Yes, locally it's the same game. You're right. Let me think.
Maybe what I think is that you need to be sure that you can construct such a network with the right.
You have constraints on the graph.
Yeah.
But you can build graphs with those constraints. That's
I think so, but maybe not all of the graphs. I don't know.
No, not all the graphs.
So
but you can forget the question.
No, it's just I would have to think about it, because I think the problem that you would get is that, so you see, this game is independent from this game. However, if I connect these 2 games here with one more restriction, that the output of one of them has to be the input of the other, they're no longer independent games. Maybe you can still do a similar reasoning, but I'm not sure you could just say that you can win all of them with only the number of communications that you have with your degree. But you could be right, it's just I never thought about it.
They're not independent because the output of one is the input of the other.
So I'm comparing this game and this game. So they're not independent here. And so far I can do it because I can choose the inputs. But then if on top of that, I add 1 connection here.
Only one of those 3 edges can be a 1 edge, and that one would go first. So you still got that ordering. You can still run the game.
Right. I think I would like to draw something, and then we can maybe discuss this after the.
We'll discuss this afterwards.
Yes. Right. So this is just an example where you would need a certain number of communication steps if you do it classically, and because this is a game where you have a non-signaling advantage, you would only need 1 round of communication if you do it the non-signaling way. Now I'm going to show you the game that gives you a quantum advantage. So this is somewhat similar to the CHSH game. It's a game that now is played between 3 parties. So you have Alice, Bob, and Charlie, and you have some referee who is going to send an input to each of the players. And this input could be 0 or 1, with the promise that if you add up all these numbers, it's going to be even. So the referee is not going to send 1, 1, 1, for instance, because that would be odd. That's a promise that we make. The referee is going to send you something that obeys this rule here. And Alice, Bob, and Charlie, they now have to produce some kind of output, A, B, and C, also 0 or 1, such that this table is obeyed. So if everyone gets input 0, the sum of their outputs should be even. And if anything else, so if they get only 1 0 as input, their output should be odd. So this is just another rule, like the CHSH rule. These are the rules for the GHZ game. And the thing is, you can also show that there is no classical strategy that can win this game. So it means that Alice, Bob, and Charlie, before getting their inputs, they cannot agree on a strategy such that after they are separated and very far away from each other, once they get their inputs, they are not going to follow those rules that they agreed on, such that the outputs are going to obey this table for all possible inputs. So it's just another game. And the thing is, there's no way to win this classically. And by win, I mean, no matter what input you get, you would provide a valid output.
Unless you communicate.
Right, unless you communicate. Because that's the thing. There is no classical solution, but with one step of communication, you're right, you can win the game. So for instance, if with this one step of communication, Bob and Charlie send to Alice their input and their whatever choice of output, there is always something that Alice can do, knowing her own input and the information from her neighbors. She can choose A accordingly. Because if you remember, the rule is that the total output should be either even or odd. This is something Alice can change with her single output. So with one step of communication, you can win this game. Now, the nice thing is that if you play this game the quantum way, you don't need communication, because if these three parties share what we call a G8Z state, so it's an entangled state for three parties, and they perform smart measurements, they will always get the correct answers. That's why it's called the G8Z game. It's a game that is made to mimic the probability distributions of a G8Z state. So you're asking a classical system to reproduce quantum correlations. That's why classically, this is very hard to do. You need communication, and the quantum way, you don't need communication.
So if I understand correctly, you're replacing a posterior classical communication with a prior quantum communication, right?
Exactly.
Okay.
Yes. So that's why when we look in the network scenario, you only need one step of communication, which is establishing the G8Z state. And if you do this the classical way, you need communication, right?
Sorry, I do not understand the figure. Is there a relation between the X, Y, and Z value that are sent to A, B, and C and the GHZ state? Or are they completely independent, and then they use the GHZ state to perform some computation,
right,
to get the result?
Okay, so maybe my drawing was not the best. You have to think that they share some GHZ state.
Okay.
And apart from that, they're also going to get inputs. They're not related to GHZ state. Next time I draw this, I'm going to make something more didactic.
This is what I was thinking.
Right. Yeah.
There is a dimension I am missing. So initially you started with this coloring problem, and you want either to build the coloring or to check. So which are large systems. So
how is this a coloring problem?
But what is the connection between this initial aim and this local structure with four items? So I'm not sure to grasp
right.
The dimension, because you started with the big dimension graph problem where you have an NP-hard thing to solve, and
right.
And so will you use that in the global structure later, or it's...
No, you're right. Maybe I should point out how this is in fact a coloring problem if you look at it the right way, because what I'm doing here is so a coloring problem is the problem where you want neighbors to have different colors. But I could define other kinds of labeling problems where the labels that I assign to my nodes, they have to obey some other rule. This is a labeling problem. It's more general than a coloring problem. And I could think of the outputs that I produce in this game as labels. I could actually think as the collection of my input and my output as a label instead of a color. And then I would have to assign this node a color, which would be input X, output A. And then the rule that I would want to obey is that whenever I have neighbors, these colors, they have to obey the G8Z game. So this is, yeah.
Okay, but what I don't see is the NPR problem. So here you have a very small number of cases, and so you save, if I get it correctly, 2 communication steps. But what I don't see is perhaps it's coming is you started by the solution of this large of computer vision problem. There is nothing like that here. That's just my.
You're right. So if we can look back at this network scenario. And indeed, this is not an NP problem. In fact, it doesn't grow with the number of nodes at all. It's just the degree of the graph. So the thing is, these are these are really the very first result where you get any task where you have a quantum advantage. We hope in the future to find a problem that is NP on a graph, but easy with quantum. We do not have that yet, and you're right, this is not an example of that, but yeah, this is just a first step, but you're right.
Can you come back to the slide? Yeah.
This one here?
The next one. Here you have one step of communication, but then you say with quantum you don't.
Oh, right, yes.
Yeah, with the DHZ state, but this matter of, in the previous case, some slide ago, don't go there, you were considering that adding the, I don't remember how you call it, in the non-signaling case, adding these
PR boxes.
It was one step of communication.
Yes.
But here, sharing the GHZ state, isn't it?
That's also, yes. That's why I didn't write here. So you would need, for the quantum case, you also need one step of quantum communication. You're right. The difference that is going to appear is just as in the CHSH network game. The advantage appears when you play it in a network, because you have to play the first and then the second and then the third.
Okay.
Yes. So I didn't start with this because now we have a very ugly hypergraph. So I have 3 people playing the GHZ game within this hyper edge that connects a trio of players. However, each of these players is also going to play their own GHZ games with other neighbors. And each of these neighbors is also going to play their GHZ games and so on and so forth. I don't have to draw the infinite graph for you to get it. And these GHZ games, they are also in this network, they are not independent. Once again, I have to play my first game because the rule that I am imposing is that the input for my second game, just like as we did before, is the output of my first game. And the input for my third game is the output for my second game, and so on and so forth. So what you get here is exactly the same scenario where if you want to do this classically, you have to communicate for every game. So you need as much steps of communications as you have neighbors. But then if you do it quantumly, you only need one step of communication, which is the step that you need to establish a GHZ game between your neighbors. Yes?
Do you consider that every agent has just 2 inbound links?
So with only 2, this is not impossible to solve. I consider at least 3, but I could not draw 3, and there's no space. But you're right, it should be at least 3 for the game to be impossible for classical without communication. Yes. Right. So that's, yes. Do you have questions? Sorry.
No, I'm just trying to figure out. So you start from a specific origin, and you have your first triangle. Then you play your thing with the output having certain properties, and then things propagate in this tree, right?
Yes.
And the steps, propagation steps, go with time. So you at each time of step, if it's discrete time, you compute the output in your tree.
Yes.
There are like 3 to the k computation taking place simultaneously. But there is a multiplicative constant, and this constant that you will divide by.
with the
Yes.
number, right?
Yes, because yeah, you only need local computations for that. And you only need local communication. You only need to talk directly to your neighbors, right? So at the end, yeah, this is going to be proportional to the degree of the graph.
Right, right, okay, but the number of computations still grows exponentially with the number of generations, right?
The number of total computations. So then if I consider all the computations that every node is doing, yes, but then what we're interested in is how many time steps you need to do that. So many of these computations are going to happen independently at the same time. So
Yes.
if you're not my neighbor, you can do your computation at the same time as I do because it's not going to interfere. So we're not interested in the number of computations, but the number of communication steps.
Because you just want to check, or do you want to build a solution?
I want to build a solution, but I can do this in parallel unless we're neighbors. And then if we're neighbors, we only need one step of communication for each game.
Yeah, so I don't get, because it seems causal. You first have to, you started with the first object,
Right.
then you give the state of the neighbors, then you go on.
Right.
Can you start?
So maybe my presentation of this graph was not the best. I'm not saying here that you're going to play this game first and then this game first. I'm just trying to draw what this is the network. This is not the game. I'm just saying what is the network that we have. So instead of putting this, at first I put something smaller just to understand what is the structure of the network, but this is what we have. And then every node here is going to get the number 1 as input, and now give me a solution. And then you only need to communicate once with each trio of neighbors to win the game, if that makes more sense. Right.
So just to make sure I got this clear, again, if you have nodes that are agents that are attributed 3, for example, then they will have 3 hyper edges, one which is phase 1, one which is phase 2, and phase 3.
Yes.
But phase 1 will always have input, I imagine 0, 0, 0.
0, 0, 0. No, 1, 1, 1. Sorry.
It has to be even.
You're right. So there's one extra rule that we did not, I did not put here because I thought it was too much. So we are expanding the JZ rules such that if the inputs, they are not the promise, you can output whatever.
Okay. But so the phase 1 hyper edges will all have static input, and then
Yes.
that input goes into edge 2, edge
Yes,
3.
exactly.
So if you have degree 3, you will only have 3 rounds.
Yes.
Of games.
Yes.
Okay.
Exactly.
Regardless of the size of the graph.
Yes,
Okay.
exactly.
Makes more sense.
Right. So everyone can play their first game together. Everyone can play their second game together. Everyone can play their third game together. Yes. So you only need 3 rounds. Yes. Right. So what I showed here with the JZ game is exactly the same intuitively that happens with the CHSH game. Because this is a hard task for classical, you get some advantage if you consider bigger theories. For CHSH, it was non-signaling, but here for the JZ game, because this is a task that is very easy for quantum, then the result that you get is you only need 1 step of communication for quantum, and you need as many neighbors as you have for numbers of steps of communication if you do it the classical way. So that's where we have the gap, the quantum advantage for this problem. Right, so this is basically the full result with a lot of details here and there and a lot of more computer science from their part. But as I said, this is the very first result that gives you a quantum advantage in a distributed problem. And there are lots of things that we can think about for the future. We're interested, for instance, in getting a problem, a task, that the separation that you have between classical and quantum does not depend on the degree of the graph, but depends on the number of the nodes. So the problem that if you have a bigger graph, you have a harder problem, which is not the case that we have. So this is something that we would like to think about. What is a task that is very hard for classical, depending on how many nodes you have, but for quantum, it should be easier. We're also interested in finding a way, an operational way to estimate quantum bounds. So when you do it the classical way, the computer scientists, maybe we can discuss this later, they have a technique called round elimination to put a lower bound to the number of classical time steps. There's nothing like that for quantum. We have a quantum bound here because we showed a strategy that only needs one step of communication. But for other problems, we don't really know how, without giving you the strategy, we don't know how to put a lower bound to the quantum communication that you need. And also, the solutions that we propose to these problems, they are very independent. I play my first game, I play my second game, I play my third game. I'm not doing any kind of joint operation. I'm not playing the 3 games together. I'm not doing, we could do more general things. Yeah, so these are only 3 of many directions that we could take with this research and that we plan to do in the future. Yeah. Yes, so thanks for listening, and I think that's enough for now.
Thank you. Any question on the bridge first? In the room?
Yeah. So I guess this is a natural question. You showed for the GHZ game that you have 1 round is enough in the quantum setting. For the CHSH game, you showed 1 round is enough in the non-signaling setting. What happens in the quantum setting for the CHSH?
So exactly, we know that for 1 game, 1 round of the game, you need 1 step of communication for quantum. We think that for quantum, you would still need 1 step of communication for each round. We have no proof of that, exactly because it's hard to find, we don't know how to find a lower bound to these problems. So it's hard to show that there is no better strategy.
But the GHZ game strategy that you use does not map for fully entangled.
It does not.
Pairs. Okay.
No. Yes.
There is a question on the discussion.
It's a thank you. It's not a question.
Thank you, Marco.
I have 2 questions. So the first question is about the execution model. So I assume that your classical model is a local model.
Yes.
Which is fully synchronous.
Yes, we're assuming synchronicity, yes.
So if we consider a more realistic model in some sense, that communication occur asynchronously, do we keep this quantum advantage?
So I don't think so. Yeah, then things get way more complicated. We did not think about that at all. We are aware of this limitation, but this is not something we're worried for this work. But you're right, I don't think this result would keep if you did asynchronous communication. We're assuming there's a clock that's ticking all the time with every node doing the right thing. This is another setting that you could consider, but it's not the one we did consider.
Okay. The other question relates to the locality. So you spent some time explaining the HCL model, the HCL kind of algorithm, but this is different from a local problem because a local problem will be HCL, but there are some HCL problems that are not local.
Right. Yes, but this one is. This is local. Sorry. Yes.
But then what is the connection with the HCL kind of problems?
So
here it's really focused on local problems that can be solved locally.
Right. So the thing with LCL is that you want, for the classical case, you want to use this technique of round elimination, and then it works for LCL. So that's why we are interested in LCL problems, because we want to prove lower bounds using round elimination.
Okay. Thank you.
You're welcome.
Other questions? Question on the bridge, last chance. So thank you again, Isadora.
Thank you. See, can I eject? Oh no, before ejecting, I have to close this. This. Thanks for
No problem.